All right, in the last video, we learned that concurrent VI schedules are the most common way to study the basics of choice and preference in a controlled laboratory context. Now we're going to see how that tool has been used to build a very fundamental understanding of behavior that kind of applies across all species and individuals. We're going to learn about something called the matching law. It's an equation, yes, sort of a simple mathematical equation that predicts choice behavior in a really powerful way. So let's start with a very elegant classic study done by Herrnstein back in the 60s. He did all these studies with pigeons, but others have replicated it with all sorts of other species. So what he did is he set pigeons up on concurrent variable interval schedules, like we talked about before, and he tried sort of different number combinations for those VI schedules. So you can see some examples in the upper right here, some example comparisons between two keys, A and B, the yellow and the green side. So the key is he set it up so that in every case, the total payoff that they could get was 40 reinforcers per hour. Like that's the maximum amount they could get if they were using both these keys, as much as possible or ideally. The most they could get is 40 reinforcers per hour, just based on the delays that are programmed into those VI schedules. So, for example, looking up at his top experiment here, the top comparison of A and B, there's a VI 3-minute schedule with another VI 3-minute schedule. So they have the choice, which of these two buttons should I push? One's on a VI 3-minute, one's on a VI 3-minute. On each schedule, you can get a maximum of 20 reinforcers per hour, or at least on average, that's what it comes out to, right? Because it's VI, it's variable. But over the hour, it averages out to 20 reinforcers if you're hitting that thing kind of about as soon as the delay ends, as soon as the timer is up. Because every 3 minutes for an hour, that comes out to paying off 20 total times. So if you're getting 20, you can get at most 20 on each side. Kind of add both of those together. That's 40 reinforcers per hour that you could get on average, right? And then look at the experiment below it. So just a different A and B choice, right? Two sides. We've got a VI 9-minute schedule and a VI 1.8-minute schedule. So one of those you have to wait less than 2 minutes on average each time to make it pay off. The other you have to wait almost 10 minutes between each payoff, right? Now, if you calculate that out per hour on average, together they total 40 reinforcers per hour, again, on average. So in all experiments, he's kind of controlled that variable. He's held that variable constant of how many total reinforcers they can get per hour. So that variable is held constant across all these comparisons. So that's not going to be what's determining their behavior. If it's different in these different experiments, it's not because of how many reinforcers per hour they can get. Now, with different concurrent schedule pairings like this, like the 4 example experiments we see here, you can calculate basically the proportion of reinforcement that comes from key A. So basically it's just a way of saying like how much better is one side than the other. Of these two keys that the pigeon can peck, how much better is key A compared to key B? So what he does, he just counts up how many reinforcers they can get from the first schedule, from key A, and he called that R sub A, R with a little a. And just to be clear here, because this might be confusing, he's using R here, the letter R, to count reinforcers. So this doesn't mean behavior response like we usually use the letter R in other contexts. Here he's literally just using R to mean reinforcers, number of reinforcers they could get per hour. So at the top of this equation, if the pigeon can get 20 reinforcers on schedule A, right, that's the most you can get on a VI 3-minute schedule. You got to wait on average 3 minutes. So for an hour, that's 3 times 20, 60 minutes. That's 20 reinforcers you can get on schedule A. That's what R sub A is. You put 20 at the top of this equation, and you can see it's just divided by the total number of reinforcers that they get across both schedules, right? So since R sub B, right, the number of reinforcers they get from key B, is also 20, the denominator here would be 20 plus 20. It'd be 40, right? So the proportion of reinforcers on key A, the proportion of payoff that you're getting from option A is 20 divided by 40, which is 1/2. So in this first experiment at the top, in his little table up here, in this first experiment comparing VI 3-minute and VI 3-minute, half of the reinforcers come from key A. which makes sense, right? 50%. That totally makes sense. So we've kind of got it off on the right side here, 50%. And of course, you can do the same thing to calculate the proportion of reinforcers coming from key B. So it's just how many reinforcers they can get from B, which we'll call R sub B, and divide it by how many total there are, which is still 40, because he said, in all experiments, he said it, so 40 is kind of the most you could possibly get. So here it'd be 20 out of 40 again, which is 1/2. Makes sense, right? You get half from key A, that means the other half comes from key B, which is totally intuitive, since for this both experiment at the top, or this first experiment at the top, both of them are VI 3-minute schedules. There's no difference between them, so of course you'll spend about half your time on each. So you can do that for each of the experiments, right? So he in this table up here, we've shown 4 experiments, 4 choice experiments between an A key and a B key. So you can do that for each of these, for each of the concurrent schedule comparisons. The next one down in the list here gives 17% of the payoff on key A and 83% on key B, right? Just plugging it into the same equation, just looking at how many reinforcers on one side out of the total. The one below that, where it's a VI 1.5 minute schedule versus an extinction, right? The side that never rewards you. That means key A gives 100% of the rewards and key B gives 0%. So the proportion, right, would be 100% on key A and 0% on key B. You kind of get the idea. That's all we've got here in this relative reinforcement column off to the right. But here's where Herrnstein's study is so cool. So he's calculated out kind of the relative payoff of the two sides for whatever choices he wants to set up. He's made the total amount of reinforcement you can get constant, but he's changed the relative rate of reinforcement between the two choices. So that's just about the setup. Now he throws pigeons in there and runs them on these different pairs of schedules. He actually runs the experiments. And again, he's going to give them a lot of experience with these two keys so they have time to figure out how they work, right? So this is going to be, he's going to look at their steady state behavior after they've done this a whole bunch and had experience with both of the choices. He ran pigeons on these different pairs of schedules. He ran each of these experiments and looked at their actual behavior to see how their behavior is controlled by the choices presented to them in their environment, specifically by the kind of relative rate of payoff between those two choices. So for each comparison, he just counted up their behavior. He calculated the rate of behavior done on each of those keys, like once they'd had a while to experience the setup and get into a steady state. So here, I'm gonna open a new column here. Here is his actual data. This new column is responses per hour. Like this is their actual behavior. In the top experiment, right, the VI 3 minutes versus a VI 3 minute, in that top experiment, they hit each of the keys 2,000 times on average. In the third experiment, if you go down to the third comparison, they hit key A 4,800 times and never key B. And so on. So this is just, you can see there's their actual behavior there. And now that he has the data for their actual behavior, he can calculate that out, just like we did before, as a proportion, right? A relative rate of behavior. So a proportion of how much behavior they allocated to each of the keys. So if we want to know, like, what's the proportion of pecks that the pigeons were putting on key A, on option A, we can calculate that out. Since he was using R for reinforcers before, he used R previously for counting how many reinforcers there are, we'll use B here to count the number of behaviors. So this B is for their actual behavior now, okay? We'll write B sub A for how many behaviors they did on key A, and B sub B, B with a little b, for how many behaviors they did on key B, on the second option. So for any key, we can calculate the proportion they did on that key. And that gives us our final column on the right side here. Like for the top experiment, what's the proportion of behavior done on key A? It's 2,000 out of the total in that experiment, which was 4,000 total behaviors. So the proportion on key A was 2,000 out of the whole 4,000, which is 1/2, 0.5, right? 1/2. Half of their behavior was on key A. What if we go down to the second experiment, right? And we want to know on key A, what's the proportion of their behavior they put there versus the other choice, right? And on key A, we see they did 250 behaviors, whereas on key B, they did 3,000 behaviors. So what proportion of their behavior was on key A in this experiment? it would be 250, but divided by the total of 3,250, like 3,250, right? So 250 divided by 3,250, which comes out to roughly 8%, right? 7 point something percent. In the third experiment, 4,800 out of the total across both options, which is 4,800. So 4,800 out of 4,800 were on key A, which is 100%, right? 1.0 is the proportion, so 100%, and so on. So we've just got the relative proportion of behavior that they put on each of those choices when we've set up the choices how we have. Now, once again, we can do the same thing for key B, right? Not just option A, but for option B, the same way. So it's just whatever proportion of behaviors wasn't on key A. It's actually just kind of the opposite of whatever our proportion was on key A. So in experiment 1, it was 50% on each, right? 50% on key A means they did 50% on key B. In experiment 2, since it was 8% on key A, that just leaves 92% that they obviously must have done on key B, which is the same thing as I could calculate it out, right? I could plug it into this very simple little equation and say, how many behaviors did they do on key B? And we've got 3,000, right? Out of the total pecking behaviors, which was 3,250 in that experiment. So on key B, they did 3,000 out of the total 3,250. That's about 92%. And if you go down to the fourth experiment, so down at the bottom of the chart, the fourth comparison, the fourth choice experiment, on key A, they did 1,750 out of the total 4,650 behaviors, which is around 31% on key A. But that leaves 69%, 0.69 is the proportion, so 69% on key B, which is the same as saying they did 3,900 behaviors on key B out of the total behaviors of 4,650, if you add those together, right? Now, the interesting thing that Herrnstein had demonstrated here is what we see when we compare those last two columns, the relative rate of reinforcement on each of our choices and the relative rate of responding on each of our two choices. And those numbers usually come out remarkably similar. Like in that fourth experiment, 33% of reinforcement can be earned on schedule A, and they ended up doing about 31% of their behaviors on that key. Now, it's not always exact, but across a wide variety of circumstances, when any individual is choosing on concurrent schedules like this, what we find, what Herrnstein found and what kind of replication studies since then have found is the relative rate of behavior will match the relative rate of reinforcement on each option. He called this the matching law. In other words, if one option gives double the reinforcers, we'll choose that option twice as much. If both options give the exact same reinforcement rate, we'll choose both of those options equally. We'll split our behavior equally. So we can formalize this with those simple equations we wrote earlier, right? So, you see this on the left here, the equation. So remember, we used B to count their behaviors. So we're saying, what do we expect their behavior to be? Or what do we see when we actually do these experiments? What do we see their behavior to be on any given choice? Like how much will they spend, how much of their behavior will they spend on option A, key A, choice A, right? Whereas R was counting how many reinforcers they can earn on that key. Again, a relative proportion, how many reinforcers they get out of the total. So it's the relative rate of reinforcement is kind of on the right side of this equation, and the relative rate of their behavior is on the left side. It's saying the proportion of behaviors on key A will equal the proportion of reinforcement that's available on key A. And that's kind of what dictates our choices. Our choices are controlled by the relative payoff of what we're choosing between. And the same logic applies to the proportion of choosing key B, right? We can run the same thing, but with sub B for the key B, looking at the green button, right? So the proportion of behaviors allocated to any choice, it's just matching the relative rate of reinforcement from that choice. So for that fourth experiment in our little chart here, you can see I've kind of highlighted in red, the relative behavior on key B was 69%. They spend about 70% of their time on key B, on option B. And that makes sense because the relative rate of reinforcement on that key was about 66%, right? It's pretty damn similar. You can actually check the math yourself for any of these. You might go through and practice, but check the math yourself by just plugging the raw data into that matching law equation. So in that bottom experiment, for example, we can say we've got R sub A and B sub A highlighted here, just meaning we've got kind of the amount of reinforcement and the amount of behavior that happened on choice A, right? On option A, the yellow key. We've got those highlighted here. We can just plug that in. And same thing, we can plug in the part for key B, right? We've got R sub B. That's how many reinforcers they did on key B, on the green key. And we've got the reinforcement available on key B. Reinforcers is the R sub B. We've got the behaviors they've done on key B, which is the B for behavior, with a sub B for the second option, meaning how many behaviors they did on the green key. So the relative rate of reinforcement would just be 13.3 divided by the total, which is 13.3 plus 26.7. So I've kind of color-coded it here in purple. That's the right side of our matching law equation, right? That is the relative reinforcement. We end up with 0.33. If you plug those in, that's the right side of our matching law equation. That's this right here. We've just calculated by doing 13.3 over 13.3 plus 26.7. Just plug that in, and we've got 0.33 on the right side. And then we can calculate the left side, their behavior, right, by looking at the data on their actual behavior. So how much relatively did they do on key A? Well, we would just plug in their behavior sub A, so B sub A, their behavior on the A key, 1750, out of 1750 plus 3900. Again, I've kind of highlighted it in purple here, but that comes out to, if you plug it in, 0.31, about 31%. So for key A, the matching law was pretty close. Same thing for key B. We can run through the same thing, and you see the matching law is pretty close. 0.66 and 0.69. So they're roughly equal. So again, for reinforcement on key B, I won't run through it all manually, but you can just see, like, we would take R sub B, which is 26.7, divide it by the total of them, comes out to 66%. For the relative rate of behavior on the green key, on the B option, we get 3,900 divided by the total, which is 69% of behaviors. So again, pretty close. That is the matching law. So we run this across a whole bunch of experiments, run it for different creatures and contexts and species. Same thing seems to happen. So the reason it's so famous and received the term law is just because the matching law really predicts choice behavior really well in a wide variety of contexts, a whole bunch of different species we've tested, using a wide variety of different reinforcers and different types of behaviors that we're looking at, not just pecking things in an operant chamber, not just pulling levers, but all sorts of behaviors, even for us humans, both in the lab and out in the field, out in the real world. And actually, just as a side effect or as a sort of side note, it works just as well if we're talking about duration style behaviors, like if we're counting time spent on activity A versus time spent on activity B, you're choosing where to spend your time on these two options. The relative amount of time you spend watching TV show A will match the relative payoff you get from TV show A. Also, in test after test, the matching law seems to apply just as well when we have more than two choices that we're choosing among. So if we're deciding between a bunch of behaviors that have different relative rates of reinforcement, we'll spend a proportion of our behavior on each of those choices that matches the proportion of reinforcement it offers relative to the other choices. So again, just a lot of ways in which it helps describe behavior. Now, as you probably already noticed, the matching law is a very close approximation, but it's not always exact, right? So we should probably write it something more like this, with an approximately equals sign in the middle rather than an equals sign. And you might say, well then, Brian, is this really a law if it's not exact? I mean, Newton's third law of motion doesn't say that for every force there's an approximately equal-ish and opposite force, right? But honestly, even Newton's laws weren't exact. So his law of universal gravitation doesn't actually describe the behavior of objects perfectly. In fact, it got updated by Einstein's theory of general relativity. So Newton's law of gravitation, it is a great and very impressive approximation, even if it's not literally exactly descriptive of how objects work in the real world. But of course, like Einstein, we want to understand nature in a more exacting way. So we want to understand where the deviations from matching are coming from when the relative rate of behavior is not exactly equal to the relative rate of reinforcement. And what causes those deviations from matching? So we've studied this for decades now. Researchers have found two sources that help account for the inexactness of that original matching law we've been talking about. So one of those sources why things don't come out exactly equal of behavior compared to the reinforcement rate is what we call bias. This is just deviations in the behavior due to some unidentified outside factor other than the rate of reinforcement that makes the individual tend to prefer one choice. So examples of this would be like if it's easier to see the red light for a particular species, right? Maybe the way their perceptual apparatus works, they can see red lights better. It stands out more. It's more salient. That would be a perceptual bias that might make them pick red a little more often than we'd expect. Or if they have a tendency to respond on their right side or on their left side. That's what's called in the research. We call it just a side bias. They seem to like that side. They do more behaviors on that side. Or something else in their past history involving those stimuli or behaviors. Like if this same pigeon ran an experiment last week where the blue key was always the good one that paid off and the green key was always the one that was on extinction and didn't pay off. Now they've kind of programmed into their brain a little bit of a love for the blue key and a little bit of hate for the green key. And if we start a new experiment using blue and green, they're going to have a bias related to those colors just based on their past history, right? So stuff like that. It's a pre-existing tendency towards one of the options. But there's also another source of deviation from matching, another thing that explains why their behavior, how they split their behavior across the options in a choice situation, doesn't exactly match the relative rate of reinforcement. So this other deviation from matching we call sensitivity. Basically, like no individual is going to be perfect at detecting differences or changes in the rate of reinforcement. Like a pigeon's brain is not a perfect computer, and it isn't keeping an exact calculation of reinforcement rates on each side, nor is the sample size of its experiment its experience necessarily large enough, or their sampling of each option perfect enough for the little pattern recognizer in their brain to perfectly calculate the rate of payoff that they've gotten from each option. Like they just don't have access to that information. So in other words, they're imperfect. They're not perfect at discriminating how much better or worse each of the options is. So even if they're trying to match their behavior to that relative rate of reinforcement, their behavior can only be allocated as accurately as their brain is able to figure out those relative rates of reinforcement, which will never be perfect. So since we can't perfectly detect the rate of reinforcement, obviously our behavior won't match it perfectly, even if the matching law is really describing how choices are made, right? So with sensitivity, one way this could go would be something we call overmatching, meaning you respond disproportionately more on the better option, and that's good. You want to respond more on the better option, but disproportionately more means you're overshooting it, right? So for example, key B, the second option, right, the green one on the right or whatever, key B might be paying off 70% of the reinforcers. So I should be spending 70% of my behavior there. If I was doing perfect matching, if I was really maximizing my payoff, I should be spending 70%, but I actually am hitting key B 85% of the time. That would be overmatching. Basically, your brain did figure out that key B is the good one, but you're kind of overdoing it on key B. That's overmatching. Your sensitivity, you were a little too sensitive, kind of. The other way your sensitivity could be off is what we call undermatching, where you respond kind of disproportionately less on the better option. So for example, if key B pays off 70% of the possible reinforcers, you should be spending about 70% of your behavior there. But if I'm hitting key B I don't know, 52% of the time, like, yeah, I slightly prefer key B, but not enough, right? I'm not sensitive enough to how good key B is. So that would be undermatching. Basically, your brain hasn't quite figured out how much better key B is. So these two things combined, bias and sensitivity, these two factors, can explain why the numbers don't always come out exact in that original matching law equation, and why that inexactness doesn't actually undermine the elegance, the beauty, the explanatory power, and the sort of the generality of that matching law idea. So you can think of it kind of visually like this idea of bias and sensitivity. The graph here in the upper left, this graph, it's a regression line just showing the relationship between like the relative rate of behavior with a B along the y-axis to the left there, and it's got the relative rate of reinforcement. So with an R for how many reinforcers you get, the relative rate, how many you got on option 1 divided by how many you got on option 2, right? That's just a ratio. So it's the relative rate of reinforcers you're getting is on the x-axis. The relative rate of behaviors, how much behavior on option 1 divided by how many behaviors you do on option 2, right? So the relative rate of behavior, that's what we're graphing out here on the x-axis and the y-axis. They're showing it on a log scale, by the way. That doesn't matter for conceptual purposes. That just makes sure that we're starting with a straight line here. So the point is, if our behavior is following the matching law exactly, so if our behavior did actually, exactly match the relative rate of reinforcement, then our behavior would be the same. It would be right on this line going up and to the right at a 45-degree angle. So that's if matching was perfect. You could think of sensitivity then as affecting the slope of the line, so the angle of the line. So in other words, their behavior doesn't kind of keep up with the difference in reinforcement. That'd be undermatching. Or their behavior overshoots the difference in reinforcement, and that would be overmatching. On the other hand, then, bias would be more affecting the intercept of the line, like just shifting the line. So if their sensitivity was perfect and had no error, imagine their sensitivity is great. The slope is the same as perfect matching. The slope is perfect, great. But the entire line might be shifted up or shifted down. In other words, shifted in general towards a preference for key A, or shifted in general towards a preference for key B, just due to some pre-existing bias. In that case, kind of regardless of reinforcement, they always have a slight extra tendency toward one of the choices, toward one of the behaviors. Now, since we've identified these main sources of deviation in actual behavior, deviation from the predictions of the matching law, can we just incorporate them into the law and thus get a more perfect prediction of behavior? The answer is yes. So to start with, we can actually take that matching law, what we saw before on the right there, we can simplify it a bit. Just mathematically, we can change it around a little to express it in a simpler way as ratios rather than proportions. So the ratio of behavior that I spend on Schedule A to behaviors on Schedule B, that would be the left side here. That's an equation of the ratio of reinforcement on Schedule A to Schedule B would be on the right there. We're saying they're equal. So this expression, what we're seeing highlighted in the left here, this is mathematically equivalent to the law that we saw before on the right side in orange here. So this is still just the matching law. What we're seeing in yellow here, we're saying the ratio of behavior on key A to key B is equal to the ratio of reinforcement on key A to key B. That's still the matching law. It's still about the relative rate of reinforcement on those, dictating the relative rate of behavior on those. Okay? So same thing, that's still the matching law. Well, now we want to extend it by incorporating bias and sensitivity into the equation. So we're going to call this thing, because it kind of accounts for everything in general, we're going to call it the generalized matching law. Something that will capture behavior even in real world contexts where individuals might have some response biases and where their brain's sensitivity to discovering the relative rate of reinforcement isn't perfect, right? That's real world. So we take that matching law equation, the ratio version that we just got there in yellow, we take that, but now we're going to add a little constant as a multiplier. That's the K that comes before the parentheses there. That's bias. And then we're going to add an exponent here, the little a, which is sensitivity. So if someone had, let's say, a large pre-existing bias to really like key A, maybe because it's green and green is their favorite color, then K would be a big number, something larger than 1, which means you'd multiply that big number by the ratio of reinforcement on key A, kind of making their actual behavior part of the equation, the very left part of the equation, have a higher ratio of behavior for key A. For sensitivity then, if that little a exponent in the top there was exactly 1, for example, that wouldn't affect the equation at all, right? Because anything raised to the 1 power stays the same. So that would be perfect sensitivity. But if that little a exponent for sensitivity, if it was, let's say, a number bigger than 1, like if it was 2, we'd be squaring the ratio. So we'd end up with overmatching, with the behavior side of the equation being unbalanced toward the key with the bigger reinforcer. Or if that little a exponent up there for sensitivity, if it's smaller than 1, we would have a lower ratio of behavior for the better schedule. In other words, we'd have undermatching. Now, the key thing here is that this generalized matching law, by simply taking into account these two factors of bias and sensitivity, it is extremely good at predicting behavior. It fits real life behavior out there in the real world super well across all sorts of contexts. Now, you might ask, where the heck do you get the number K to plug in for bias? And where do you get the number A to plug in for sensitivity? Right? Where do we get those numbers? If we're going to plug them into this generalized matching law to predict someone's behavior, what numbers do you throw in there? And the answer is we determine those empirically. Like the only way to know if a particular monkey has a color preference for green is to test it with different colors and see if it has a color preference for green. The only way to know if a dog has a side preference, a side bias, and just has kind of a slight tendency to prefer things on its left is to test it. So we can quantify those things. We can get estimates of those values by collecting some data. Same with sensitivity. Put a pigeon in a bunch of experiments, kind of like Herrnstein did, and see how well it can pick up the relative rate of reinforcement in each of those experiments. Compare that to a different pigeon or a specific rat or a particular chimp or to little Johnny or to different adult humans. Each individual will have a different sensitivity. And we can just calculate what that is for each individual. And of course, some species may be more sensitive than others to pinpointing exact reinforcement ratios and things like that. But we can calculate that. And once we do, we can plug those numbers into the generalized matching law. We can predict the individual's behavior then in a wide variety of novel choice situations. Now, we won't dive too much into plugging specific numbers for bias or sensitivity, but just to help you kind of visualize things conceptually, we can go back to how we were graphing it out before, where perfect matching with no bias and perfect sensitivity, that would be a line going up and to the right at a 45-degree angle. So as we can see kind of in the left side versions of each of these. So the higher the ratio of reinforcers on choice A to choice B, the higher rate of behavior on choice A to choice B. That would be the plain old matching law if there's no bias and no sensitivity. Now, the higher you go on the x-axis, right, the higher on the y-axis. That's all we're talking about. That's why it's like a correlation line, right? It's a nice simple regression line. But now we can look at the top half of this figure. So just these three panels in the top half here. If bias, the k, right, our value for bias k is greater than 1, like in the middle panel here, you can see their actual behavior gets shifted up toward higher values on the y-axis, a higher ratio of behavior on choice A. If the bias value is less than 1, that would shift the line away from perfect matching, but toward doing kind of relatively fewer behaviors on choice A and more on choice B. So regardless of reinforcement proportions, regardless of the x-axis value, bias just makes their choice, their y-axis value, always be a little bit extra in the direction of one of those behaviors, one of those choices, right? On the other hand, sensitivity could be graphed like we see in the bottom half of this figure. So the bottom three panels here. Sensitivity changes the slope. It changes the angle of their behavior when we graph it out this way. So as the reinforcement proportion goes up, in other words, as the x-axis goes right, as we go further to the right on the x-axis, we get more reinforcement proportionally on key A than we do on key B. As that happens, the behavior either goes up too far, which is overmatching, or it doesn't go up far enough, which is undermatching. So that's where you see if the A value, meaning the actual sensitivity value, if that little a, the exponent, is greater than 1, we get overmatching. So the angle is too high. They're really spending too much of their behavior on choice A relative to choice B compared to how much they should be getting from the relative rate of reinforcement of those. So we've kind of shifted the angle way too steep if the sensitivity rate is greater than 1. If it's less than 1, you get the opposite. You get undermatching, right? So another way to put it, like if you look at this, when the x-axis is negative, in other words, when the reinforcement proportion sucks for choice A, then undermatching means too much behavior for the sucky choice, and overmatching means too little behavior for the sucky choice. In other words, you could just think of overmatching as an overreaction, and undermatching is an underreaction to the actual real rates of reinforcement that those choices would give you. So if we account for both bias and sensitivity, then we get an incredibly good prediction of how people behave and fundamentally what's at the heart of it, right? Once you've accounted for bias and accounted for sensitivity, you're predicting their behavior incredibly well just by knowing they will make their choices, they will develop their preferences based on the relative rate of reinforcement. That's how our choice seems to work. So that's enough math for now. What we've seen is just all else being equal, our choices are dictated by the rate of reinforcement that we get from the options available to us. In some sense, we are all just pigeons in a giant complicated Skinner box, where at any given moment, our choice is between behaviors like studying or watching TV or going to the gym or playing video games or eating healthy or eating poorly or whatever else, right? We've got a bunch of choices in front of us. And what we see with the generalized matching law is, all else being equal, our behavior gets distributed according to the relative schedules of reinforcement. Our choices are controlled by our environment. Now, in the next couple of videos, we'll really look deeper at the applications of this stuff in terms of things like self-control in our behavior and issues like behavioral economics.